So not all logarithm expressions are written in either base 10 or base e, which are calculator friendly. On your calculator, if you're working with a regular scientific or a non-Inspire graphing calculator, you're going to have a log button and you're going to have an ln button. So you're going to have a log base 10 button, you're going to have a log base e, a natural log button, but you're not going to have a log base 3 button or a log base 8 button. But we still want to be able to calculate what those logarithm values are. And so fortunately we have something called the change of base formula. And so in that change of base formula we have a mechanism for rewriting a logarithm from one base into a base of any other that we choose. And so typically we're going to choose to rewrite it in either base 10 or base e so that we can figure out what that result is using our calculator. So if we take this first example, log base 3 of 24, we can generate an estimate for ourselves as to what that value is by what we've done before, maybe setting this equal to a and then rewriting it as a exponential. So if I rewrite this as an exponential, the base of my exponential 3 is going to match the base of my logarithm. A logarithm is an exponent, so it's going to be 3 to the a equals 24. Now that obviously I can't figure out without a calculator. 24 is not a power of 3. It's not so easy as just dividing both sides by 3 to solve for a. I need to figure out what exponent a needs to be in order to make this work. Well, 3 squared would give us 9. 3 to the third would give us 27. So what we can see from this is our answer for a, whatever this number is, needs to be somewhere between 2 and 3. It's going to be some sort of irrational decimal value. So the way we can figure out what that number is by using the change of base formula to rewrite this in either base 10 logs or base e logs and then use our calculator to solve. So I'm going to go ahead and do it both ways. So I can rewrite this as base 10 logs and I just use the pattern that I see here. So whatever is in my, that I'm taking the log of is going to go into the numerator. So I'm going to say log base 10 or just log of 24 over, and now whatever my base is, that goes into the denominator. So I'm going to take the log of that in the denominator. So log of, in this case, 3. And so now I'm going to go to my calculator, push buttons to solve. So on my calculator, I'm going to type in log of 24, and we get 1.380 if I round off to the nearest thousandth. And then if I do log of 3, I'm going to get 0.477 if I round that off. And then if I take that answer, or those two answers, and divide them, I'm going to get 2.892, which, again, going back to what we did over here, we said we should get an answer that's somewhere between 2 and 3, and so indeed we did. Now, we could have done the exact same thing, but instead of converting things into base 10 logs, instead we could have converted both of those, or our expression, into natural logs. So if I scroll down here, so I'm going to use the exact same pattern where this number that I'm taking the log of is going to be in the numerator, whatever my base is going to be in the denominator. So instead of log of 24 over log of 3, I'm going to do the natural log of 24 over the natural log of 3. And so I'm going to do those two calculations. Natural log of 24 is 3.178. We round off to the nearest thousandth. And then the natural log of 3 is 1.098, or 99. Sorry if I round off correctly. And so then if I take those two answers and divide them, I'm going to get 2.89. It rounds off to 3. So we end up getting the same answer. Yes, we're off down here, but it's because of our rounding errors. We can see that it doesn't matter whether we round off or use the common logarithms or the natural logarithms. We're going to get the same result using this change of base formula. For the second example, we'll only do this one once, and I'm just going to go ahead and change it to natural logs instead of the common logs, just for variety's sake. And so I'm going to follow the same pattern that we see up here. So the number that is we're taking the log of, that's going to go to the numerator. The base of our logarithm is going to go to the denominator. So I'm going to rewrite this as the natural log of 80 over the natural log of 8. And so I go to my calculator, I push buttons, natural log of 80 is 4.382, and then I take the natural log of 8. On my calculator I get 2.079, and now I take those two numbers and divide them, and we end up with a result of 2.107. Now if we want to confirm that that's correct, we could do it again by using the common log button instead of using natural logs, or we can do a similar thing to what we did on the previous problem. If I rewrite this as an exponential expression, I can come up with an estimate as to what my answer should look like. So if I say again, like this equals a, and rewrite it as an exponential, base of my logarithm becomes the base of my exponential, so 8 to the a power has to equal 80. Clearly, the answer is not 10. If I raise 8 to the 10th power, I'm definitely not going to get 80. Well, 8 to the second power is 64, too small. 8 to the third power is definitely bigger than that. It's 512. So that means my answer for A should again be, like it was in the previous one, somewhere between 2 and 3. This time, though, we end up with an answer that's a little bit closer to 2, which makes sense based on where we see this fitting in between these two. So we can feel pretty confident at this point that that 2.107 is the correct exponent, the correct answer.